Okay, thank you very much.
Awesome. Now we have Xavier Rival on resource analysis.
Okay, so hello everybody, and thanks for coming to this session preview for the resource analysis session. So since the topic is a little bit less wide than what David was presenting, I decided to spend a bit more time on the background and a bit less time on the paper. So first I will try to give you a few keys to this area, which is still quite a diverse area. So the idea is to look at resource. So what is resource? So first of all, we have to look into what the target property of the analysis that we are going to consider are. So usually we want to check that a program will at most use certain amount of resource, typically time, sometimes memory, could be also energy. Actually, there are cases where you would like to know that the program will at least use some amount of energy, typically if you want to protect certain things and you want to make some work hard for someone else. Maybe you would like to look at average, which is going to bring some interesting question. We are going to see that a little bit later. Or maybe you don't even have a bound that is given a priori to you, and you just would like to compute a bound on the maximum or average amount of resource that your program will consume. Okay, so that's kind of the target property. Now, if we look at the analysis design steps, actually the analysis design step is something that is quite general. It's not specific to resource. So let's see what you're typically doing. Typically, you start with the semantics. So today we have to make this semantics resource aware, of course, if we want to talk about resource. So semantics will often have to be a little bit non-standard. Then you typically have to choose a target property. And target property will be quite interesting because of this average thing. When it shows up, we'll see that sometimes it makes things a little bit more interesting. You have to fix an abstraction and then some analysis algorithm, like could be abstract interpretation-based static analysis, type checking, type inference, deductive proof, and whatnot, okay? And very often, oops, sorry, I would like to remove this thing in the bottom. Ah, that's great, sorry, I apologize for that. Yeah, I just want this one. Good. So I will make essentially 3 points that seem to be specifically prominent in this area. So the first one is to look a little bit into the logic that is going to let us reason about resource. And I will mention one concept that's quite important, which is the concept of linearity. Okay. After that, since we, as I said, we are going to talk about average. When you have to talk about average, very often you have to measure things. And this is where probability theory very often, very naturally comes up. And last, I will spend just a couple of minutes mentioning what kind of analysis algorithms you may want to use. And as we will see, very often you just have to use off-the-shelf algorithms that you are going to just have to make work for the resource reasoning. Okay, so let's start with the logic side. So the big question here is how to make logic count resource. So I will spend a little bit of time on a concept that's called linearity because I think it's very important. So the idea is that if you look at classical logic like we have been doing for centuries, if you want to prove that A0 and A1 is true with some assumption gamma, you just try to prove both of these with the same assumption gamma. And in the 80s, a number of people, including Jean-Yves Girard, brought up what is called linear logic, which is to just depart from this classical principle and to introduce another form of conjunction, which is called linear, in the sense that in order to prove A0 times A1, this time you have to just count the assumption you have, and you cannot quite use the same assumption twice. So you just have to split your set of assumptions. Some of it will prove A0, will be used to prove A0, and the rest for A1, okay? And this principle gives way to a whole logic with connectors, not only for conjunction, but also disjunction. Some of them are classical, like this one. Others are linear, and there are a few operators called exponentials that control weakening and also contraction, okay? So what are the applications of that? Why are we talking about this? Well, first, if you look into proof theory, controlling when you can duplicate proof arguments like that has big implications on proof search and on the cost of proof search. Okay, so this is the first point where resource is showing up. Another is if you take the well-known Curie-Howard correspondence between proofs and programs, what you are going to get when you look at the distinction between those two proof principles is a control of the duplication of terms when you do beta reduction. And that gives you an immediate entry into logic to reason over the complexity of programs. So there are, for instance, logics to talk about polynomial time algorithms. Okay? So next, linearity has been actually generalized and extended to many other situations. So there are logics to reason about various resources in a linear way. One that is common, we talked about it yesterday, Philippa mentioned separation logic, which is very popular for heap. And actually we have the same kind of connectors, like classical and separating, except that now the resource is heap space. Okay? So now that we have this kind of principle, we can use logic to talk about programs in a resource-aware fashion. The second point that is quite important in this field is to count, especially when you have average. So in finite case, average is fairly simple. When you have to look into continuous case, you have to actually do some sum and to have some measurability over your space, and this gives an entry into the probability theory, which is actually a tool that is going to be used in many of the papers that we are going to see in this session, okay? So because of that, you have to look at probabilistic transition systems, generalization of Markov chains. You have to also look into probabilistic semantics. I guess I don't have time to discuss this more. So now I would just mention the last point I wanted to bring up, which is that once you have the logics, once you have the measurability if you need, because you are talking about average, which is not the case of all the talks, then you have to also look into analysis algorithms. And actually in this area, I would just make the point very quickly. Very often you have to use conventional analysis for different purposes to reason over your programs, to answer certain questions that will let you later answer the resource question. Okay, so now I will very briefly discuss the three papers. So the first one is going to set up a probabilistic resource-aware session type system. So the idea is to perform automatic amortized reasoning over probabilistic systems with some amount of communication. And here you will see an extension of types with probabilities and also some inference algorithms with constraint solving. Okay? So that, which allows you to get some, to automatically infer some properties on amortized runtime. Second paper is about a calculus for amortized expected runtime. So here also we are going to talk about amortized runtime for programs, but this time a big focus of this paper is to work on randomized data structures. And here again, linearity is going to show up both in the resource counting and also in the heap, because we are looking into the data structure. So this paper is focusing very much on some variant of separation logic that is going to have some probability built into it, which allows to reason over programs that manipulate randomized data structures in a probabilistic way. Okay? So, and based on that, this paper constructs a precondition calculus in the horse type. Okay? Which is okay, finally, the last paper is about a general non-interference policy for polynomial time. So here again, we look at, we try to, so here, unlike the other two works, we try to find upper bounds for computation costs and to characterize polynomial time programs in some class of language. And here, what is very original is to rely on some other kind of analysis, which is going to infer properties on information flows using shape analysis to reason over complex data structure to isolate what is going to cost loop iteration. And actually, in fact, behind this, the underlying brick is very much based on the linearity principle I mentioned. Okay, so I think I don't have time left, so resource is over. And I just invite you to look at this session to get more information.